Hello everyone, and welcome back to the third and final part of Python testing with PyTest motivations, demonstrations and practices. In the previous parts we have introduced tests, we've motivated why they're useful, we've introduced PyTest, given a brief demonstration of it, and introduced what fixtures are, and a rudimentary way of parameterizing tests. In this video I'm going to talk about how to parallelize Python tests with PyTest using pytest-xdist, and I'm also going to talk a bit about isolating sections of code to run tests, why we want to do that, and a demonstration of it using the pytest-mock library. I'm going to wrap up by concluding with some quick-fire thoughts about useful things I've encountered while testing and while developing in Python. So let's get into the example. You might recognize this because it's exactly the same example we had at the end of the previous video, but I'm going to kind of go over it again for the purposes of filling in the people who have joined in this one. So we have a function, an integer to binary function that takes an integer and returns a binary string and adds some zero padding to it. The zero padding is not particularly relevant for this example, mind you. We have a fixture which has three sets of parameters in here, which means that this test will run 3 times, once for each parameter, and will give us a result at the end, which is great. So now I'm going to run these tests, and I'm actually going to close this window, and we're going to do it this way. So to demonstrate that the test and the software seem to work, I run my PyTest on my Python script, and the tests all pass, and that's great. Now, parallelization. The simple example is to just stick -n and auto on the end of your PyTest execution when you have pytest-xdist installed. This means Python, or PyTest, will automatically try to determine how many compute nodes you want, and this typically equates to the number of cores in your computer. So we can see from the output, you can see my plugin list here. We have xdist installed and we're running Python 3 in case anyone was in doubt. We have spawned 4 compute processes, 0, 1, 2 and 3, and we've scheduled our tests and the tests have all passed. Now this may look pretty simple, and to an extent it really is, but remember why we're running parallel tests. We're running parallel tests because we want to make our tests execute faster. Now, the top example shows that the 3 tests pass in about half a second. The bottom example shows that the 3 tests pass almost instantaneously. So in this case, actually running the tests in parallel has not gained us any speed. In fact, it's lost us time. Now, parallel computing is fraught with complication. It requires a deep understanding of the material. So the reason the parallel version here has taken longer is because we need time to set up all of the nodes, to start Python processes on all of the nodes. We need time to schedule all the tests. We need time to collect all the results at the end. And these little intricacies kind of add up. Parallel computing is for big problems. That's kind of the key message I want to get across with this example. So in order to really get a flavour for what's going on when you're running tests in parallel, I need to run them with the verbose flag. So here we can see our 3 nodes get spun up. We can see that they're running Python and where they're running, which is good. We can see that they have started. We can see what node runs what test. So in this case, 0 runs test 0, 1 runs test 1, and 2 runs test 2. And 3 just sits there doing nothing, so it's effectively wasted. If you're so inclined, you can also control the number of processes you start. So here we're testing with only 2. So in this case, 1 node runs 2 tests. So node 0 has run test case 0 and test case 2. I think that's a fairly simple explanation for what's going on here. So in summary, pytest-xdist allows us to distribute tests to other compute nodes, typically local cores, but can also distribute to other machines as well, and cores on those machines. PyTest can guess the number of cores you need, but there's a catch with this. So this isn't really part of the summary, it's more just kind of dump, I suppose. If your software is kind of compute-intensive simulation software, it's probably going to be running in parallel anyway. With that in mind, you probably don't want your tests to run in parallel as well, because your code will also already be running as efficiently as possible. So what you can alternatively do, using xdist, is to make your parallel software run as you would normally run tests, and use pytest-xdist to test serial regions. This applies if you're spawning threads or forking your main process or whatever it is you're doing. You do need to be aware of parallelism and potential pitfalls there are, but the speed gains can be tremendous. So I'm going to come back to parallelism a bit in the fifth example. So this is our final example where I'm talking about software in isolation, and we move on from our binary converter example. So I've made there are quite a few steps here. You'll notice I have two files open this time. I have my simulation library file, which is independent of my test file, and the simulation library has a run simulation function that reads parameters from a file, does some work on them, so I'm basically doing time sleep, which is wait a second, to simulate that we're actually waiting a second for the results to compute, and we return the results of our very complicated calculation. I think it's pretty simple. So the expectation is that parameters.txt contains an integer. Straightforward, I think. So test simulation library is designed to test the run simulation function only. We have our fixture because we're good people, and we've parameterized our fixture with 10 example parameters. Now this is kind of redundant, but it's useful to demonstrate the feature of parameterization, and I am going to try and parallelize this, and we'll come on to why that's not a good idea in a minute. So our test function opens the file and writes the parameter data to it. Pretty simple. So if this test is called with fixture 1, it will write 1. If it's called with 5, it will write 5, and so on. With the file written, it runs the simulation, removes the parameters file, and then checks the output matches what we want. I think that's pretty straightforward. Or at least I hope it is. So let's run this in serial. So no xdist, no parallel running at all. So we collect 10 items. The tests run slowly because each one is waiting a second. So in this case, it's quite slow. You know, we had to wait 10.05 seconds for all our simulation tests to run. But they passed, which is good because it shows that our library and tests are in cohesion with each other. So, if we're naive, we just bang on the kind of a -n auto on the end and we expect everything to be alright, right? Well, life is not quite so simple. We have failing tests and we have a lot of output. We have 8 failed tests, though the tests have run faster, which is of some consolation. I'm just scrolling up here. So we can see we have in test simulation 3, so that's the third parameter case. We have a file not found error. It's not found the parameters file, presumably because another version of the script has removed the parameters file by the time it got here. Test simulation 0 has got an incorrect assertion, presumably because it's read the file from test simulation 3 instead of. So it wrote the file, and then test simulation 3 wrote the file, and it performed the wrong computation, which is a shame. And we're basically in a bit of a mess. You know, we have files flying everywhere, we have parallel tests failing. It would be nice if we could just test run simulation in isolation. So now I'm going to do a brief interlude and talk a bit about test types. Now these definitions are very loose about what I'm going to say. They have formal definitions in the literature, but for the purpose of an easy explanation, I'm just going to describe them in a kind of human grokkable way. There are 3 core types of tests. There are unit tests, these guys on the left, integration tests, the guy in the middle, and the system tests on the right. The unit tests are designed to test functionality of individual blocks of software. The advantage means we can introspect deeper and understand more why something has gone wrong. The downside is we don't really get to see things at the system level. We're quite removed from what the user can see when we're running unit tests. System tests, on the other hand, the tests on the right, test everything that the user can do, and is quite good at determining whether or not the user is going to run into a problem. But they're not very useful for determining what's gone wrong. Unit tests in general are better for that because they can introspect deeper into a single bit of code. Between these two, we have the integration tests, and the integration tests test the relationship between two blocks of code to see whether or not they mesh well together and behave as you would expect. They don't test things on the user level, and they don't test things on the module level, more the connection between modules. So unit tests are useful because they allow us to look at small, look on finer grained detail about why something has failed, but all three of these test types are useful. In this case, we just want to test the run simulation function. We don't care about read parameters because, let's say, it's very basic, we can see how it works, and we can test that separately using a different function. So we want to isolate run simulation. We can do this using mocking, and I've got a mock example in here somewhere. Yes, there it is. You'll notice that this is quite a bit shorter than the previous one. Well, a few lines shorter, so it feels simpler on the surface. What we've done, instead of creating a file and then removing that file when we're done, we instead patch. So this mocker argument here is something specific to pytest-mock, and what it will cause pytest to do is give us access to all of these juicy mocker functions, one of which is patch. So what this does is it hot swaps simulation library .read parameters, i.e. this reading function, with a different function. So this is kind of a hot swap where if simulation library.read parameters is called by anything, we'll instead run this function. So this is a lambda function, just to clarify. What this function will do is, whenever it's called, it just returns the input data, which is whatever's passed to the test. Pretty simple. So when we run, the theory is, when we run our simulation library run simulation function, it will just, instead of running read parameters up here, it will run our side effect function here. That way we're not creating or deleting files, and we're just testing run simulation. We're not testing read parameters, which is very useful. So let's see if it works. So it's collected 10 items again, and again we're waiting 1 second between each one, and it's very slow. Wouldn't it be nice if we could parallelize these tests? Well, last time we tried to do that, it kind of blew up. So it would be nice to know that it's going to work. We can see we're not doing any file input-output, so we know we're not likely to crash into any other processes. So let's give this a go and see what happens. So we've distributed our tests, and they run one block of 4, one block of 2, and another block of 4, and we've passed all of our tests in 3.6 seconds. So in this case, using the parallelization and the mocking together has allowed us to test run simulation, which we wouldn't have been able to do otherwise using the kind of core basic methods we've already covered. So to summarize, mocking allows you to kind of hot swap one function with another. It doesn't matter where that function is, we hot swap it. The interesting thing about this example that we've just covered is simulation library.py hasn't changed at all. It's the same file that's being called by both tests. So mocking is a way of changing the behavior of something else in order to test something specific. We can test individual behaviors of complicated functions. We've talked a bit about different test types and how mocking allows us to control stuff, and we have learnt a somewhat harsh lesson about parallelism and how we need to be careful with it. So that's the end of the code examples. So now we're entering the wrap-up stage, where I typically rush at the end of a presentation to say lots of things very quickly. This is a list of topics that I didn't get round to talking about, but I would like to give them a brief mention. So pytest is not the only Python testing framework. Neither is Unit Test or Nose. There are more out there. There are many out there, and they all have interesting development histories and relationships. If you're looking at using Python for a big project and you're looking into testing, I recommend looking at more than just PyTest for your testing needs. Though, for me, PyTest has done everything I've needed it to. I recommend looking at other projects too. The pytest timeout module is useful for catching when tests time out. So if you're waiting for a socket connection, or accidentally you're waiting for some user input or something like this, pytest timeout will allow you to catch timeouts in an elegant way in the pytest framework. Beyond pytest, PDB or IPDB is a debugger that you can use in Python in order to step through code line by line. And you can use this with PyTest in order to explore a bit more about why something fails. Debugging is a big topic in and of itself. I'd like to give it a talk at some other point in the future, but it's a very useful tool, and I recommend looking it up at least if you're not aware of it. The pytest COV module is useful for code coverage. So code coverage is kind of the school of thought that if we're testing more of our code, our tests are generally better. And this module will show you whether or not you're testing a certain line of code. It will show you what percentage of code you're testing and things like this. Very useful if you have a lot of conditional blocks and you want to test complex branching code. Aside from testing, general software development practice, I recommend version control. There are many other options to version control and many options within version control, but they basically allow you to divide up your changes into single blocks or commits or whatever you like, which means that you can test specific commits of code to make sure they work. It's a good way of demarcating change sets, amongst other things. Continuous integration ties well in with this, so Jenkins, BuildBot, CircleCI, Teams, Itis, Stuff, Bitbucket, Stuff, Atlassian, and whatever. There are very many tools that allow you to do this. The idea is somebody working on their code can just commit and push to a version control repository, and the CI server, or continuous integration server, detects that the code has been pushed, runs the tests, and sends an angry email if they failed. And this way, the developer more quickly knows whether they've made a mistake. Git bisect is something very specific. It basically allows you to perform interval bisection search between two commits. So if you see one change set, if you're on a change set and you know the tests have failed, and you can see that there's a change set far back in the past where the tests pass, Git bisect allows you to do an automated interval bisection test to see which exact commit caused the test to fail. It's quite a useful tool in my opinion. The JUnit XML flag plays well with Jenkins and various CI tools to dump test results, and basically anything that goes into conftest.py allows you to kind of break the rules of PyTest, or the core rules of PyTest, and allows you to do all kinds of interesting things that generally a very cool thing to look at, in my opinion. So let me summarize the entire talk. Testing software is essential, but bad tests are really destructive. And that's kind of a takeaway message. If you write tests and you don't know that they are incorrect, you will be led down the garden path, and that's not good. But the gold mine is tests that work well, and tests that do what you want, and tests that you can maintain. There are many approaches to testing. I mean, even in the parameterization example within PyTest, there are many ways of doing it. I found PyTest works and it's good for me, but there are many other options, and many other projects use a variety of different things. My last kind of cautionary warning is, yes, the testing rabbit hole is deep. If you are on a project and you're really enthused by my talk and my kind of activity and enthusiasm that you want to integrate testing, beware, it takes time. And you need to budget your time carefully, because if you spend 90% of your time writing tests and 10% of your time writing code, you're probably doing something wrong. It's easy to optimize tests, thinking, oh, I need this feature in my tests, or I need this feature in my tests. It's very easy to fall into that trap, and I warn against well, I warn that you should budget your time if you're looking into do this for a serious project. So, thank you very much for listening to my talk. You can get PyTest using pip or conda or at pytest.org. The presentation slides are available as a release binary on the presentation repository you can see here. I'm quite active on GitHub if you want to get hold of me. I'm MVOUSDEN. I'm also on Twitter at mvalsden2 if you want to tweet me, and I'm also contactable by email. The link is coming soon because my YouTube channel is not yet famous and I don't have a permanent link, but that's how life works. If you do have any questions or you do want to get in touch, feel free to do so. The Southampton Python User Group page can be accessed by link from these repositories. I'll also put a link to them in the description of this video. Thank you very much for joining me on this journey through PyTest, and hopefully I will see you next time on a future video. Thank you for watching.